Okay, in this lecture we're going to talk about finding zeros of polynomial functions. A zero is an x value that that identifies where a graph of a polynomial actually crosses the x-axis. Sometimes we call it the root of an equation because it's the answer to the polynomial here, the y value being 0, so it's actually the answer of this being equal to 0 if this was the case. Now, as we already have seen, that if I have even a number, say 12 divided by 3, we know that's 4, and it's exact, so there's 0 remainder. Alright, that tells me that 3 is a factor, and we know that 3 times 4 is actually 12. Now we can do the same thing with polynomials. We already have seen the remainder theorem, and the remainder theorem said that if k, alright, or when I divide it by x minus k, for example, alright, using synthetic division, then the f of k value was the remainder, and if the k value actually came out to be 0, then that meant a 0 remainder, which means that this thing goes exactly into the polynomial, divides exactly into the polynomial. And that leads us to the factor theorem that says that this polynomial x minus k is a factor of f of x if in fact we have f of k is equal to 0. Conversely, if f of k is equal to 0, then this will be a factor. And we're going to use that to actually factor polynomials that are of higher degree than 2. We already know how to do degree 2 polynomials by factoring or using the quadratic formula and so forth. Now, in this case here, to find zeros, alright, we're going to first of all use the factor theorem to see whether this is a factor, alright, by seeing whether in fact we get a 0 remainder. And to do that, we set up our synthetic division. This time we have k as identified as -4. Right, remember it was always opposite. And now let's put down the coefficients. Notice there's no cubed coefficient, so we put 0. -48, 8, and 32. And bring the 3 down, multiply by -4 gives me -12, adding gives -12, multiply by -4 and -12 gives me 48. Add, I get 0, -4 by 0 is 0 of course, add I get 8, -4 by 8 is -32. Adding I get 0. Notice that this of course is f of -4, and this is equal to 0, so that's going to imply then that x plus 4 is a factor of f of x, okay, by the factor theorem. Okay, now if I didn't get a 0 here, then it would not be a factor. Okay, right, let's look at the next one. Let's look at g of x now as this particular polynomial, and we're going to look again to see whether x minus 4 is a factor. So again we have k is -4. So let's put this in here. Put our coefficients of g. Looks like they're all there this time. Okay, again we bring our 1 down, multiply by -4 gives me -4. And I get add here, I get 2. -4 by 2 is -8. Add, I get 3. -4 by 3 is -12. Add, I get 0. -4 by 0 is 0, so I get add, I get 5. And here I get -20. When I add, I get -40. And this of course is g of -4 now. And notice that this is not equal to 0. So x plus 4 is not a factor of g of x. Okay. Now a couple of other things I want you to notice here is that when we do the synthetic division, this was a exponent of 4, and it will produce a polynomial of degree or exponent 3. Okay, this one was degree 4, and so doing the synthetic division drops it down 1. This one is degree 5, and this one here produced would be degree 4. Now this is significant because if we want to factor a polynomial of higher degree than 2, then we can use synthetic division to reduce the degree. This is particularly useful in cubics because if I have a factor, like in this case here, we have a factor here of 5. So we want to, sorry, 5 is a 0, but we want to find all the linear factors. Well, if 5 is a 0, then x minus 5 is a factor. Okay. And so consequently now, if we now apply our synthetic division, we will reduce this cubic polynomial down to a square of degree 2, which is a quadratic, which we know how to solve. Right, so let's see if we can actually factor this cubic into linear factors. We have one linear factor, so x. So when k is 5, we have a 0. So we have here, if we put all of our coefficients here, we put a 5 here as a 0. So then we have a 6 as a cubic, we have a negative 37 as a squared, we have a 32 and a 15. So we've got all the coefficients. Bring the 6 down, multiply by 5 gives me 30, gives me negative 7. This gives me 5 by negative 7 is negative 35. Add here, I get negative 3. And 5 by negative 3 is negative 15. When I add, I get 0. So that verifies that this x minus 5 is a factor. Right, but more importantly, we now have this quadratic, x squared minus 7x minus 3, and we can factor this. And let's see if we can factor it. Alright, and can be factored here. So let's have a look and see. We would want factors of 6 by negative 3, negative 18, which are going to add to negative 7. And straight away we see that would imply that we'd have negative 9 and 2. So we'd make this here 6x squared minus 9x plus 2x minus 3. Okay, so that's what this would become. And this now becomes, if I take out a 3x, I'll end up with a 2x take 3. And if I take out a 1 here, I get a 2x take 3. If I now take out a 2x take 3, I end up with 3x plus 1. Right, hence my function f of x equals 6x cubed minus 37x squared plus 32x plus 15 can be factored into x take 5, of course the one we've given, the 2x take 3, and 3x plus 1. And so we now have the 3 linear factors that can be multiplied to make up this cubic, and this of course leads us to all of the zeros. Alright, 5 here, and of course if I solve this to be equal to 0, I'd end up with 3 on 2. And in this one, I'd have negative 1/3. And so I have the 3 zeros and I have the 3 factors, which is rather useful. And this is a great way to reduce our higher degree polynomials until we get to a squared. But of course, we're going to need to know how to actually find some zeros to be able to reduce it.